Good afternoon, everyone. Hello. We hope you had a great day so far. We are super happy to be in Berlin again, and it's always a great atmosphere here. Hi, my name is Oskar Neumann. I'm a solutions architect at AWS.
And hi, I'm Dirk. I'm also a solutions architect here at AWS. Before we start with the actual talk, I would be interested in who in the audience here joined one of the hands-on workshops that we ran across the city in Berlin yesterday, the event we called AWS Housewarming. Who did join? Can I see some hands? That's a few. Amazing. Thanks for joining. Please be aware that you actively participated in the world premiere of AWS Housewarming. So that's great, and that's something nobody can take away from you anymore. And if you did participate, also please let us know if you liked it, if you want us to do it again, and if we should do it again, what should we do differently? All right. One other remark regarding the housekeeping and the logistics. Oskar and I are going to split the talk among each other, so we're going to deliver it in turns. Oskar is going to start with the first part, I continue with the second part, Oskar third, me fourth, and that's it. Okay. Oskar, take it away.
Thank you very much, Dirk. Okay, so today we want to talk a bit about the value that loosely coupled event-driven architectures can bring to the table, but we want to do that not only from the technical perspective, but also from the business perspective. And to make this all more tangible, we decorate our talk with some real-world scenarios and use a fictional customer as a vehicle for those. And we also use this opportunity to discuss various integration patterns that are the foundation for loosely coupled event-driven architectures. And talking about the many different phases of integration is really important because every modern company, or every company also, needs to deal with integration scenarios. And this is not only in many layers, but also in many areas, as you can see on this picture. And of course, this also does apply to our fictional customer. So let me introduce you to them. And you might have heard about them before. They're called Wild Rides. They are all over the news right now. And they are a technology startup from Berlin that disrupts individual passenger transportation by replacing traditional taxi cabs with unicorns, of course. And this is because unicorns are a lot more fun and also more magical. So this company has two founders, which I would like to introduce to you right now, which you see here, Ozzy and Dirk. Unfortunately, we have to respect their privacy, so we had to make their faces unrecognizable. But both of these founders have innovation on their minds, and they want to move fast, and they really don't like the self-introduced constraints from their technical architecture. But let them speak for themselves. Ozzy and Dirk say, to be ahead of competitors, we need a tech architecture that unlocks business agility. This includes the ability to run experiments with unknown scaling requirements easily, or to add components to production workloads with minimal effort and pain. This is why they have already started an architecture evolution. But let's rewind a few months back and have a look at the starting situation of their software architecture, which you can see here. This is obviously a monolith. And this is what our sample customer has started with. And their all-in-one monolithic application eventually gave them a really hard time, as also with many companies and quite some pain. And monolithic applications often grow over time. And you have a lack of encapsulation in their components. So this can manifest, you maybe know it as spaghetti code, or an increase in coupling between components, and decrease in cohesion with every component. So this has obviously a negative impact on several quality criteria. And this is a driver for the companies to go to maybe a microservice approach or to self-contained systems. And in such a tradition, components from the monolith turn into independent services. That's also a good opportunity to work on the encapsulation and fix maybe the existing decomposition. And how is that done typically? Well, a typical starting point is that you carve out a sample service that either brings you a lot of pain or is seen as easy to begin with. In any case, if you deconstruct this monolith, this leads to a new integration scenario, right? Because now the resulting services need to interact with each other. And the scenario will look maybe more like this at some point in time. So there's a number of systems in your landscape, and those will have to be integrated with each other and interact with each other. And some of them have closer interactions, as you can see here from the physical distance, while others are further away, meaning they have less interaction, as you can see here with the blue circles. And the challenge to integrate these various systems is not only restricted to microservices. You also have companies that use external systems or SaaS solutions that are more far away. So whatever the scope is, you need to integrate your system, and it's a constant concern for reaching your goals, right? So let's underline this by the following quote from Gregor Hoppe. In modern cloud application, integration isn't an afterthought. It's an integral part of the application architecture and the software delivery lifecycle. Gregor is, among other books, the co-author of the book Enterprise Integration Patterns, which is a sample catalog for integration patterns. So we will also show you a few patterns from his book during our talk today. And with this introduction, I'm handing over to Dirk, who will now give you an insight how an X monolith can reach your business agility goals and how you can integrate it. So Dirk, over to you. Thank you very much.
Awesome. Thank you, Oskar. And before I do that, maybe directly a disclaimer also to underpin what Gregor says here. There is really no silver bullet in software architecture. That means every architecture decision comes with a trade-off. And this is particularly true for integration scenarios. So you should always be well aware of your constraints and your requirements and then compare the options on the table to pick the one that comes with the least trade-off. All right. So once you have a landscape of services, and one of the ideas from the beginning probably was that you can evolve and operate those services independently from each other. But unfortunately, companies still often do not reach that goal, or they also don't reach the goal to remove other problems they had with their monolithic application. Because despite of a now clean separation of concerns and high cohesion, there still can be a lot of coupling between services, and that can potentially cause problems. Let's use a sample use case to illustrate this. And this use case is called pre-booking campaigns. What is it all about? So Wild Rides have an active marketing team, and they like to run marketing campaigns all the time. Well, they like to do that, but they cannot always do it from their technical architecture that lies behind it. And this campaign should motivate customers to pre-book their rides, their future rides, already at an earlier point in time, pay for it already in advance, and get a discount for that. And let's have a look about the current high-level architecture for this use case. So I'm going to walk you through that architecture, and it all starts with the end customer. The end customer uses the Wild Rides customer app, types in all the details for the pre-booking, and pushes the submit button. And then the request, according request, lands in the right booking service. Okay. Since we broke down our monolith into a landscape of services, the right booking service cannot solve everything that has to be done on its own, but it has to utilize also other services. And the first one that gets also involved is the unicorn management service. Probably it needs to make up a unicorn that is available at that requested point in time. And the processing of that request takes a little bit. It can send the response back to the ride booking service. We also said customers should pay in advance for it, so we need to involve the ride payment service. Processing takes a little bit. It involves also the fraud detection service. And then also an external payment service provider is involved to simplify it for wild rides, which also takes a little bit of time. And then lastly, we recently also added a customer loyalty program to wild rides. So the loyalty service is also involved here, which takes a little bit of time. While all this is going on, not only the customer is waiting for a response, but also the ride booking service has resources to spend on waiting for all the other services. And this is actually the observation that Ozzy, one of the co-founders, took out of this architecture. When a service hits its limits and needs to scale out, we observe that preceding services in a request chain require scaling too. That's not exactly what wild rides actually wanted to reach, is it? They wanted to be able to scale and operate every service independently from the others. And one of the pain points in the monolith was exactly that they had to scale out everything when there were only a few hotspots that required it. But why is that so? Well, due to the similarity to synchronous function calls that were most likely used in the monolith, it seems to be a natural approach to architect also for synchronous communication via APIs over the network between the newly created services. Particularly when those synchronous APIs follow the REST architectural style. So if you have hypermedia APIs, that actually shouldn't be a problem because that leads to a loosely coupled system conceptually and from an API perspective, that is. But what happens at runtime? Well, we can distinguish between two basic sorts of communication, one-way and synchronous request response here. And as said, the obvious approach is to translate local function calls into interactions over the network and use HTTP connections as a communication channel. For one-way communication, as we can see on the left, a sender doesn't expect a response from the receiver besides an acknowledgement that the sample message has arrived. But now, for synchronous request response, as we can see it on the right, it blocks resources on the sender side while it waits for the receiver to respond back. And when a request reaches an entire application from the outside, as we have just seen it in the sample architecture, processing often involves multiple services along a request path. And this is spawned throughout the application. And let's have a look at it again to have it more tangible. So synchronous communication blocks resources in all involved services, and worst case, for the time the entire processing takes. And additionally, problems in downstream services can actually lead to, can also fire upstream and put the entire application at jeopardy. And this is why we have mitigation patterns like circuit breaker in the first place. All right, now what can we do about it? We have the synchronous request response behavior or pattern now. Maybe we can do a different kind of communication over APIs. Well, yes, we can. Asynchronous communication, as we can see it now on the right-hand side. It reduces temporary coupling to a minimum along the request path. And looking at the interaction of services, the sender only sends out a request to the receiver. It directly acknowledges that it has received the request and then can do the processing. And there is no more runtime coupling between those services. Only at a later point in time, when the receiver is done with the request processing, it needs to open up another HTTP connection in our example to send back the result. Due to the similarity with synchronous function calls, I mentioned it before, development teams tend to perceive synchronous communication between services simpler to implement, as simpler to architect for, while asynchronous communication requires some additional considerations. Well, that's true. However, there are standard patterns that help with that, and there's a lot of description about those patterns available. And in concrete terms, basically, you need to employ the two patterns that are listed here also, return address and correlation ID. And this is, in the end, only a piece of meta information that the request sender injects into the message, and it instructs the receiver where to send the response to. And it also instructs the receiver, hey, here's a unique correlation ID, please feed it back in your response so I can assign it to my previous request. Okay, so let's apply asynchronous communication to our use case. It starts like it did before. The request hits the ride booking service, and now we only have asynchronous communication. So the ride booking service receives immediately the responses. We can also respond to the client much quicker. And by the way, looking at HTTP, we now respond with 202 accepted and not 201 created anymore. And the same applies to the other services further down the line, the fraud detection service. Maybe the external service provider doesn't support an asynchronous communication. Maybe it's more old-fashioned or so. But other than that, everything else is asynchronous. And we have reduced the runtime coupling to a minimum. And this experience brings us to the following quote. Friends don't let friends rely on synchronous integration. Unfortunately, and I'm really sorry to say this, even after turning an API-based integration from synchronous to asynchronous communication, there's still coupling involved that can lead to problems. Let's look at it again. So one aspect here is the location dependency. Every request sender needs to know the location of its request receivers. Apparently, you cannot send out an HTTP request when you don't know the target address. That also means adding more receivers, removing receivers, changing receivers will lead to code and/or configuration change. And another aspect is the availability dependency. Also quite obvious, you cannot send an HTTP request to some destination that is not online. And this is also a problem that can occur when one of the target services is overwhelmed by spiky request patterns, or it is in planned or unplanned maintenance. In all these cases, request senders need to manage retry and mitigation techniques. What can we do about this? Well, the concept of messaging systems addresses this and can further reduce coupling. Let's have a look at how the communication with messaging is different from the communication via APIs. And let's start again with one-way communication. As said, with APIs, you still have the location and availability dependency. And the decisive difference with messaging comes with message channels, which are separate components. And as you can see on the right-hand side, the sender just sends a message to the message channel, and that's it. And the same applies to the receiver. It just receives the message from the channel, and that's it. The message channel decouples both sides from each other. And that also means both parties don't even have to know about each other. And the same applies to asynchronous request response. So both sides, again, don't have to know anything about each other. Looking at the location aspect, using message channels, a request sender can now act on top of business logic. And that means the semantics of a channel it sends messages to, and not anymore the technical details about their communication partners. The locations of those are not relevant for the request sender anymore. And each request receiver can autonomously decide to consume messages from the channel. Looking at the messages as such, we can also discuss the message intent patterns. You can see it here, command, document, and event message, which is quite self-explanatory. Looking at the summary of one-way and asynchronous request-response communication via messaging, we can also point out integration versus conversation patterns. A message channel that describes how a sender and a receiver can be integrated is surprise and integration pattern. And in contrast to that, the composite of a request channel, a response channel, correlation ID, return address spawns a communication between parties, and we can call it a conversation pattern. Now, I have talked a lot about message channel in a generic way, and let me hand it over back to Oskar to put more flesh to the bone with it.
Thank you very much, Dirk. So let's take a look back at the use case that we had previously, and show me once more where we ended before. So this is where we have ended, and we have implemented here asynchronous communication already using APIs. But there are still some things that can go wrong. For example, a service in the chain can get overwhelmed. Maybe the right payment service is such a candidate that gets overwhelmed. And we might not want to scale out indefinitely also. If you imagine targeting on VMs or containers, you cannot scale them out indefinitely at some point in time. Also, maybe you have some account-related limits, for example, with lambda scaling and concurrency. Maybe you also have constraints from an external service, such as the downstream payment service, that throttles you if you push too many requests through. And yeah, so let's take a look at the business requirement. We need a resilient architecture in general, but particularly, we want to run experiments with unknown scaling requirements. So how can we achieve the ability to run experiments with unknown scaling requirements? Well, let's look at a concrete type of message channel, which Dirk explained. In this case, point-to-point channels implemented using queues. What are the characteristics of queues? As you can see on the left-hand side, every message that is sent to the queue goes to one of the available receivers. So the consumers compete against each other, which you can also call a competing consumer pattern, because multiple receivers can get the messages. That also means that if you have high loads in your queue, you can use the queue to balance it out and just add more consumer processes. In that sense, the queue also acts as a kind of load balancer. Also, queues can typically buffer messages. So you can use a queue also to flatten a peak load during a marketing campaign, or just process the messages at your own pace. So in that sense, we have the queue as load balancer, and the queue also removes the availability dependency, because we no longer need to send the message directly to the receiver, but only to the queue, which is always available in the best case over an API. On the right-hand side, you can now see some AWS services you can use to implement that pattern. The most prominent choice here is obviously Amazon SQS, which is a massively scalable cloud-native and serverless service. A fun fact here, SQS was actually the first AWS service, so you can see how important it is in the internet today. However, if you are constrained to some industry standards like JSM or AMQP, we also have Amazon MQ. Going back to our example, let's see how we can decouple the services using queues. So we are simplifying the view now to make it more easy to read. So we get rid of the services on the far right, which brings us here. We still have the asynchronous HTTP requests that go to each downstream service. As you remember, a queue is a point-to-point channel. So we are now replacing these requests with dedicated messages over dedicated queues, which you can see here. Now by doing this, as I mentioned, the write booking service is no longer talking directly to the downstream services. Together with the queue characteristics, we now eliminate, as I mentioned, the availability dependency. And since Wild Writes is an AWS customer already, they also want to use the scale and simplicity of Amazon SQS. SQS is easy to use over a simple API, and it scales automatically to millions of messages per second. So, as an example, during Prime Day last year, Amazon SQS set a new traffic record by processing more than 70 million messages per second at peak. And I mean, we said so far that Wild Writes should just offload the availability dependency to a messaging system and forget about it. But this is easy to say, because you want to have the responsibility of making the messaging system available in the hands of someone who does that for a living. And Amazon SQS is so convenient compared to the attempt to do that yourself in this case. Okay, so next, the message goes to the request queue, to the downstream services. And then finally, we also expect some responses back, obviously. So we also add the response queue. Now we can scale and update the services also independently, as we have eliminated the availability dependency. If one of these services fails, is overwhelmed or unavailable, or just uses the limit of the resource spent, we can process the messages at another point in time, or just consume slower, or just add additional processes and consume faster. But how do the downstream services know where to send their responses to? And also, how does the write booking service know which response message belongs to which request? Well, Dirk already explained a pattern we can use here, which is the correlation ID and return address. And both patterns relate to meta information that we just inject into the message. And now that we got the downstream services decoupled, let's also take a closer look under the hood of the write booking service itself. Maybe there's an opportunity to decouple even more things within that service. So just for your context, we are looking at this write booking service here and zoom into the architecture, how we can decouple the activities in the service with queues. So let's forget about the downstream services for a bit and just take a look at this example use case. Let's assume Wild Rides runs a marketing campaign with the call to action, book this week. So they want you to book your ride for the next week already sometime during this week. Which with such a call to action, we obviously only have moderate traffic to the ride management service. So an architecture like this could be a good fit. We don't need any internal decoupling. The requests just hit an API gateway, which then invokes a processing step and maybe a data store in the end. But what about if our marketing team now has the idea with this new call to action, book your ride for next week already today and receive a discount? Well, then maybe we have more traffic and need to prepare for it with internal decoupling. So we now split the work on the incoming pre-booking requests between a pre-processing step and the actual processing. The pre-processing mainly does a quick sanity check and then passes it over. And if everything looks good, it goes into the pre-processing queue and the response is sent back to the end user client. Now, the actual processing takes a bit more time, but that's fine. We just have it processed asynchronously. And for the user experience, it's only important that the response to the end client comes back quickly. But what if we have now a marketing campaign that says, book now? So maybe during an ad break, on TV or something like that. They offer an additional discount if you book your ride right now for the next week. So this now results in massive traffic spikes. How can we cope with that? Well, we decouple even more and add another queue, the pre-booking submission queue. So requests that hit the API gateway are just transformed to a new message for this queue and then immediately return. This flattens the peak load for the pre-processing, so we can make sure that it doesn't overwhelm this resource with a massive load that hopefully comes in if the campaign is successful. Further down the line, we still have the decoupling between pre-processing and processing to make sure that we fail fast in this situation. All of this unlocks the business agility to write rides, which is great, but there's still more. Dirk, what else could Ozzy and Derek want?
Let's have a look. Thank you. Okay, and we just stick with this sample use case because it's so nice to exploit it. So most definitely, Ozzy and Derek want more support for their business agility. And we stay with this use case once more. This is where our current architecture evolution brought us to. And we have asynchronous integration via messaging, and with queues, it gives us resiliency and removes the availability dependency. Now, Ozzy is chiming in again with a statement. We want to add components to our production workloads with minimal effort and pain. And this is a fair requirement, isn't it? What Wildbright's experience today is whenever they want to add a new service to an application, someone needs to talk to and coordinate with all the involved parties. And this is a significant effort and eats time and resources that they would rather invest in new feature development. So we have already introduced the queues to decouple upstream from downstream services, and that's great. But what we see here is the ride booking service is still somewhat aware of the downstream parties. Although it doesn't have to know anything about the concrete consumer services behind the queues it is feeding, it is still aware of the semantics and the amount of direct downstream targets. Because it sends probably typed messages into each of those queues we see here. And it means that we also need to make the ride booking service aware if we want to add another direct downstream service. Make aware, on the other end, probably results in code and configuration change, which is an effort which we would actually like to avoid. But why is that so? Because we still work with the concept of request and response, which is only natural looking at the evolution that we went through. So tech teams typically send specific request messages to each of those target services. What we are not doing yet is to think in events. And to have some progress here, let's have a look at another kind of message channel. We already know about point-to-point message channels, which are implemented by queues. And the different type of message channel is public subscribe or fan out, implemented by topics. And those have a different behavior. Now, every message is consumed by every process on the right-hand side, and those processes are now called subscribers, because we are in the publish-subscribe pattern. Topics work a little bit like radio stations. So when you turn on your FM radio, not sure if anyone here still knows what FM radio is, but if you turn on your FM radio, you can consume all the content that is published. If you turn it off, you stop consuming the content and you will miss everything that is shared until you turn it on again. This may or may not be unfortunate, but imagine if you run into the forest and shout out loud the answer to Life's the Universe and all the rest, and nobody's there with you to hear it, then this valuable information is unfortunately lost. Okay, so with the semantics of topics, it basically raises two questions. The first one is how can we scale our consumers on the right-hand side? Because if one of those processes is overwhelmed by the traffic on the topic, we cannot just add another process, because that additional process would also consume every message. So that doesn't work. And the other question is, how can we make sure that we don't miss messages while our receivers are offline, for instance, for planned or unplanned maintenance? Let's park these questions for a bit and look at the AWS services that implement this pattern. With Amazon SNS, we have a cloud-native and serverless service that implements publish-subscribe channels. Similar to Amazon SQS, it is cloud-native and serverless, and it comes with the least possible heavy lifting. However, if you are in a migration context or constrained to industry standards like AMQP or JMS, there's also Amazon MQ for topics. And for the sake of completeness, let me also mention that the AWS IoT core service comes with a message broker that supports MQTT even over WebSockets, and HTTPS for publish only. All of this targeting apps in the IoT context, but also in the mobile context. If you have ever heard of our Innovator Island workshop, in one of the labs, it is also used to send notifications to mobile clients. All right, now, how does this all help with the requirements that Ozzy formulated a few minutes ago? Let me share it once again with you. We want to add components to our production workloads with minimal effort and pain. So let's revisit the most recent state once more. So this is where we ended. And we are still thinking in requests, and particularly in typed requests that are specific for each downstream service. And when we want to think more in events than in requests, we would just send out a message that indicates that a pre-booking has happened. So with the respective details attached, of course. And then it is quite obvious that this message would be the same one for each of the downstream services. But with the architecture on display, the write booking service would have to have the unpleasant job of sending the same message 3 times, each time to a different queue. So let's check if a PubSub channel can help us here. And we are just again defaulting to Amazon SQS in the example, as we did with Amazon SNS in this example, as we did with Amazon SQS for queues. Since SNS is cloud native and serverless, it's simple to use and minimizes the undifferentiated heavy lifting. So we now have a topic on Amazon SNS that all target services can autonomously subscribe to. And the write booking service only has to send one generic event message without the need to know who is listening. And what this also means is if there is an additional component or service that is interested in those events, it can just subscribe to the channel. Let's imagine we just recently added the customer loyalty program to Wild Rides, and the customer loyalty service wasn't there last week or so. We could have just added it by letting it subscribe to this topic. But we don't want to blindly replace our queues with a topic and consequently lose the resilience and the availability decoupling that we got from queues before. Do we? No, I think we don't, but there's a solution for this also. And this brings you the best of both worlds. And it also brings the answer to the 2 questions that we raised before. How can we avoid missing messages while we are not listening for whatever reason? And how can we scale consumers in a PubSub scenario? Well, topic queue chaining, this is the name of this pattern, is a composite pattern that, surprise, chains topics and queues. A producer sends a message into a topic as before, but then the subscribers don't directly subscribe to the topic, but they put a queue in between. So with this, we get the durable subscriber pattern that makes sure we don't miss any messages, and we get the concurrent consumer pattern that allows us to scale out on the consumer side. And this is how it looks like for our sample use case. So again, the best of both worlds. And maybe one remark here, a requirement that Wild Rides have is that it is easy and painless to add more systems to an application. And with the write booking service sending event messages into a PubSub channel, it doesn't have to know anything about the downstream services listening to this channel, of course. But however, if it wants to have some processing downstream and receives the response later, it of course needs to add some code for taking in the response and processing it. After all, there's no magic in software architecture, or at least it would come with a price. So before we take one last look under the hood of the write booking service, I need to share yet another variant of PubSub channels with you, of course, which is the message bus. Now, what's the difference between topics and buses? And the unpleasant part here is there's a whole lot of ambiguity attached to that. And you will notice it when I often say typically, often, and so on. So compared to topics, a message bus is typically used in a broader scope. You typically use a dedicated topic in a use case or a micro use case even with 2 types of parties involved. And this also helps to reduce the blast radius. And in such a context, a publisher is usually a publisher only, and a subscriber is a subscriber only. And the message bus is rather used in a more broader scope across an entire application or even across applications where a lot of parties exchange data with each other. And this is also the reason why often the involved parties act both as producers and consumers, so you could also call them prosumers. Finally, message bus products typically are more feature-rich than topics, but they may also come with a few constraints, like that your constraints regarding the format of the payload. For instance, you will typically find a content-based router functionality in a message bus. And hey, with Amazon SNS, you can also filter by content since a few months, and this adds even more ambiguity in selecting the right type of product. However, the recommended AWS service for using a message bus is Amazon Event Bridge, which is again cloud native and serverless, just like Amazon SQS and Amazon SNS. And whether it is Amazon SNS or Amazon Event Bridge for you, the best choice, it depends on the constraints that you have on your use case and so on, and all the trade-offs you can or want to make. And for guidance, of course, you can always discuss this with your friendly solutions architect in AWS. The decisive part, doesn't matter if it is topics or if it is an event bus, is that you have similar requirements for business agility, what Ozzy just mentioned, and that you think in decoupling and asynchronous communication. Now, let's have once more a look under the hood of the ride booking service, and this time taking also the downstream services into account and bring it all together with PubSub. So we have again the same details inside of the ride booking service, along with the internal decoupling. And we can use the topic queue chaining pattern internally and externally. And that means the pre-booking, pre-processing resource only has to send one message now into that new pre-booking arrived topic. And from there, the buffer queues in front of the downstream services can subscribe to the topic, as well as the pre-booking processing queue inside of the ride management service. Another interesting aspect that we can see here in this diagram is also who is responsible for that messaging infrastructure. And typically, you want to have that topics that we see here in the responsibility of the ride booking service, while the queues in front of the downstream services already belong to the consumer processes, and they would be in the responsibility of those downstream services. All right. So with that, let's look once more on the initial statement that Ozzy and Derek have made about their business agility requirements. And with everything we have discussed, we have helped them to evolve their architecture to make all this happen. And we hope this evolution was also helpful for you. And with that, we are almost at the end of the talk. But let's first have a look at a few resources and a call to action for you, dear audience. So for us, messaging and event-driven goes under the serverless umbrella. So why don't you check out the serverless learning opportunities that come along with AWS Skill Builder and the many serverless learning resources on serverless land. There you will also find material in courses about modern application development. And since the book and the patterns from the book have been mentioned a few times, I'm also sharing a link here on the online summary for enterprise integration patterns. You can just follow the link here. I'll pause a second, so if you want to take a pic. And other than that, we can only thank you for coming and your attention today. As always, we want to improve ourselves, so please fill out the session survey. Also, please feel free to reach out to us on social media. You can also approach us during the afternoon. We'll be around here in the summit. And once again, thank you so much for coming. Enjoy the rest of the Berlin Summit, and bye-bye.
Thank you very much.